Now we are going to talk about the space of solutions of a second-order differential equation. So the word space here is exactly the same as in linear algebra. So it is going to be a vector space. So first of all, notice that the initial value problem for a second-order differential equation, it is similar, but at the same time different than the initial value problem for first-order differential equation. So recall that for a first-order differential equation, the initial value problem consists of the differential equation itself and the initial condition that specifies the value of the unknown function at a given point. But for a second-order differential equation, we need to specify the value of the first derivative at the unknown point. So here is an example of an initial value problem. And again, of course, the big theorem here is that every initial value problem of a second-order differential equation again has a unique solution. Since we are talking about linear equations, that's why the unique solution is on the same interval where the coefficients of the differential equation belong, right? So we are assuming that the coefficients p, q, and g they are defined on a certain interval, right? And then the initial value of the independent variable belongs to this interval, so then we conclude that there is a unique solution on the same interval. So so this part about the same interval is what we are not going to be able to prove. But I think you kind of, because of a similarity with first-order differential equations, I think you'll believe me if I tell you that it is going to be like this. Uniqueness and existence actually holds for even for non-linear second-order equations, but the same interval is only for linear. So now the intuition here is that since in order to specify a solution you need two conditions. So the initial condition contains of two equations, right? So you need to specify the initial value of the function and the initial value of the first derivative. And since there are two of them, it means that the general solution of a second-order differential equation should be a two-parametric family of functions. All right. Here is why it is true. It is not a foolproof. Again, so this is because the explanation that I'm going to show now doesn't cover the fact that the interval of the solution, where the solution is defined, is the same as the interval where the coefficients are defined. But anyway, so here we kind of replace the single differential equation of second order with a system of differential equations of first order. So why is this true? So notice that, so look at this part. So if y prime equals z, then z prime equals y prime prime, which is y double prime. So in other words, this second differential equation tells us that y double prime equals whatever this is, and this right-hand side is exactly the same as this. And so that's why the system of two first-order differential equations that we just constructed is actually the same in a way. I mean that it has the same solutions. So if y satisfies the original second-order ODE, then the same function y satisfies the system if you let z to be the derivative of y, and vice versa. If some two functions y and z satisfy the system, then if you just delete z and just look at y, then y satisfies the original single differential equation. But then, of course, the initial condition for the second order differential equation translates into an initial condition for the system. And now notice that the existence and uniqueness theorem for a second order differential equation follows from the existence and uniqueness theorem for a system of two first order differential equations. And if you carefully analyze the proof of the uniqueness and existence theorem that we constructed last week, then you will see that actually it works almost without any change for systems of differential equations rather than for single differential equations. So that's why, although it is kind of a sketch, but it is almost a full proof of the theorem of existence and uniqueness. Again, I want to emphasize that the only thing that we are not able to prove is the fact that the interval where the solutions are defined is exactly the same as the interval where coefficients are defined only for linear differential equations.